Hi, everyone. Thank you for coming to my presentation. My name is Alexey Agapitov. I'm a principal software engineer at Zalando. And today I would like to show you how you could create code metrics specific for your app and for your project. And I named the presentation Code Metrics for your app because I thought it sounds catchy, but actually you can scratch the app part and the code metrics would still be relevant almost for any project. The only app-specific part would be is what we actually are going to measure. And then you can actually also scratch the code part, and the technique or maybe a principle for defining the metrics that I'm going to explain is also applicable for other situations, like whether those are performance metrics, or maybe you are actually working on resolving certain incident and need to gather some data to understand what's actually happening in production. Let's look into what we're going to discuss today, right? So first I would like to explain which metrics I actually would like to introduce, right? So what are these, why are they needed? Explain why would we even bother with something like metrics, so and then also elaborate it further into why we would want to develop something custom and not just use something existing already in the industry. Then I would like to walk you through the one example from my experience in Zalando, like how we defined the metrics for the modularization, how we iterated to find the right one of them to find the right one, and in the end I will talk a bit how you can actually implement it on your side. So what I would like to achieve with this presentation is that if whenever you need to do something similar, you need to find some metrics for whatever task that you have, so that hopefully this knowledge would be useful for you. And I also want to show that actually defining these custom metrics is not that complicated. So with some simple and rudimentary techniques, you can actually do it in your own project. So which metrics do I mean here? So metrics in this context are measurements of characteristics or certain qualities of your project. So these could be certain architecture qualities, so whether these modularity, scalability, and so on and so on. Or you might be more familiar with the metrics of the tech debt, right? So there are a lot of existing static analysis in industry which just traverse through your code base, collect certain maybe security issues, maybe code smells, and then they give you the insights. Okay, how much time would it take to resolve all those metrics, or how many of them you are, and like how are you progressing in resolving those, right? So what I'm not going to talk today, and what you might be sick of hearing, OKRs, KPIs, and other pirate metrics. So this is not what I would like to define today, right? So we are not going to look into this. We will try to keep it very practical. Then, why would we even bother with defining the metrics? So we already have a lot of things to work with, a lot of things to deliver. But there are many different situations in a developer's life where you might be, let's say, faced with a huge project and you are not familiar with it, or maybe the project which evolves rather quickly. Many teams are contributing to it, and you are losing your grasp on what's actually happening in the project. And then having these metrics will allow you to actually understand what's happening. So where is the project going? Is it still following the architecture that we defined for ourselves, right? You might have maybe a legacy code base where you have so many issues that you don't know where do I even start. So what is the most important metric for me? So, or what is the most important problem when there are so many of these, right? So having the data to actually quantify the problems helps you to actually prioritize them. And it's also often useful to show it to your management, for example, to pitch, okay, you know, this is the most important problem, we should focus on it, and we should solve it as soon as possible. And one of very, very nice side effects is that by having these metrics and by having visibility around these metrics, you can actually track progress of your work, right? So you can show the impact of your work. And this also helps you as a developer to estimate what is the size of the effort, whether it is a migration, whether it's a refactoring or something else. And it also gives you more credibility, for example, in discussions with the management. So you have experience, you know how to take a decision, and you know how to demonstrate to someone who might not have all your experience that this is the right decision and this is the right problem to solve. Let's talk about what already exists in the industry, right? So there is this book called Accelerate, which already defines, I would say this is already accepted book in industry, which defines maturity of software projects. And for example, it talks about certain metrics like the build time, why is it important, and how all these metrics are interconnected together and how you can measure them to, prove or ensure that your project is in a mature state or moving towards the mature state. So the metric that we might be defining, developing, they would be contributing to those bigger metrics. So something like maturity is not easy to define, right? So it could be it could be subjective, but having objective metrics behind it actually helps you to make it kind of objective and have some better understanding around it. Then some of the metrics that exist in the industry, they could be useful in general, so they might tell you how much maybe tech debt that you have, but it doesn't necessarily tell where exact issue in your particular project is, or you cannot compare different qualities of your project so that you can understand, okay, let's tackle problem A and not problem B. So for example, cyclomantic complexity is good, but does it help me, for example, to address the pitfalls of my project or pitfalls in the architecture of my project? There are some of the metrics which might be too complex to implement, like not implement, but to calculate, so cohesion, coupling. These are the things which, if you, for example, look at the fundamentals of software architecture, you'll see that they have a rather complicated formulas, right? So this is not something that you can just quickly, sketch in a Python script, run over your project and get those numbers out, right? So unless you have a software which was actually built to calculate those things, it also wouldn't tell you much, right? Then, why would we then invent our own metrics, right? So as I already mentioned, so you could look at the same problem or you could measure the same problem with different metrics. So this means is that if you might have, let's say, some more generic or holistic metric which explains maybe the whole project, but you might want to zoom in on one particular issue which is happening, and you want to measure that, okay, we're actually resolving this issue, right? So whatever we're doing helps us to avoid it in the future. And then, like, the problem with the generic metrics is that sometimes they don't know anything about your project. They don't know anything that you're struggling with. And that's why, each project has its unique challenges, right? So we have, let's say, different architectures which you could follow, right? You have different history of the evolution of the project. You have different legacy code bases, or you might have a different target architecture. So you are moving from architecture A to architecture B. And like these generic tools, they cannot answer how to get there, right? And then some of the tools might not even exist, right? So for the same reason, so you might need to develop something custom for yourself, or maybe those tools could be too expensive to buy, right? So they might not be affordable maybe at this current point of time, or maybe they are not, it's not reasonable to spend this amount of money for these metrics. But thankfully, like, we can still find ways to work around it, and we can find the metrics which would be relevant for us as developers. Now let's look at how would you actually approach this problem, right? So if you need to define a set of metrics, how would you start it, right? So the primary thing in this whole process is that you need to start with the problem, right? Understanding of the problem is the half of the solution, that's what they say. So if you don't know, if you don't have a goal, or you don't have at least abstract understanding what is your problem of your project, it doesn't make sense to even start the metrics, right? So keep in mind that metrics are not the goal in itself. They are just a tool to measure if you are actually working, let's say, on your plan. So you're following your plan, and the work that you do, it actually has the impact that you expect it should have. And once we are clear with the problem or a goal at hand, let's try to formulate the hypothesis. So what is causing the problems in our project? So what is maybe, what makes the build time so slow? Or maybe what is preventing in our architecture to achieve what we would like to achieve? Or maybe what is missing, and what is the size of the effort we know from where we are and where we want to go. So what is the size of the effort to go there? And obviously, the metrics, they need to be measurable, right? So if you cannot measure it, how can you actually see the impact of your work? How can you see that the improvements they're actually doing, they're actually improvements and not degrading something else? So maybe you improve the build times, but you make something else worse. And they should be objective in the sense that if you're working in a team, your whole team needs to be able to understand them. They need to be able to agree that these are actually the right metrics. You should be able to explain them what do these metrics mean. And then once you have an alignment in the team, you are all working towards the same goal, and you all have the same visibility that this is our goal, this is how we are, this is where we are on this path towards this goal. And these metrics, they need to be actionable, right? So if you find something that you don't know what to do about, probably this is not the right metric, so it doesn't really make sense. So you want to have some sort of the minimum set of metrics which you can actually do something about. And I think another next iteration of this technique would be is to verify that the set of metrics that you have defined is actually correct. Maybe you're thinking about the problem from one angle, but maybe there is another angle which you haven't considered, and you need to have another set of metrics to make sure that by improving something else, you make something else worse. If you found this contradiction between two sets of metrics, you need to go back to the step 2, and using all these learnings, you reiterate and find the new right set of metrics. And then, hopefully, after these 4 steps, you have, let's say, a clear definition of the problem, how to measure it, and you kind of already know what you are going to do with it. And having some sort of the guardrail metrics just to make sure that these additional things that might become worse in this process, that they are not becoming worse, you can measure them. That's why you would like to have this optionally, this set of the guardrail metrics. Now, let's look at the example from my experience. I will just follow the same approach that I described here earlier, and I will explain how I tackled the modularization issue, right? What was the goal? The goal was to have a fast compilation. And how do we achieve fast compilation? What is the architecture that is going to allow us this? Is the kernel and plugins architecture, right? So with this architecture, we can enable the work of multiple teams in parallel so that they don't conflict with each other. So the work of one team does not necessarily impact the work of another team. And that's why, for example, it's good both from the build time optimization and also from the architectural point of view. And it also works with the goals of the business when you have many different teams working on the same code base. It reduces the chances of conflicts between them and also the impact. So if you're working on a feature A, you don't necessarily need to pull the changes for feature B, and it means you don't have to necessarily recompile all the changes from the feature B because it's not relevant for what you're currently focusing on. So having this in mind, let's try to think, okay, how can we measure that we are working towards this modularization goal, right? We started at Zalando with very few modules, right? It was 1, then 2, then 3. And later, we started pulling out the features out of this, the initial module that we had into first features, then platform capabilities, and so on and so on. And at some point, we arrived at a stage of the project where we have a lot of the modules, but the monolith that was our initial application, it's still pretty big, and it still takes a lot of time. And it contains the features which are not on the hot path, so you're not actually actively working with them, so maybe you get back to them once in a year or very rarely. And that's why the modularization of this monolith, it kind of goes down. So the efforts, we did a lot of the initial effort, and the later efforts, they kind of slowed down, and we're not progressing much further. And so what is the cost of having this monolith in the app is that, first of all, on itself, it takes a lot of time to compile, but if you have a lot of modules which depend on this monolith, right, they also need to be recompiled every time it's changing. So that means that whenever the monolith changes, a lot of other modules have to be recompiled, which means that a huge chunk of the app needs to be recompiled. So although you are working in your tiny domain of a feature, in the incremental changes it might be fine, but whenever, for example, you pull the main branch, everything goes into you can just run the build, go for a coffee, come back, hopefully it will be ready for you. And this is not the situation you want to be in, right? So as I said, we wanted the work of the different teams to be running in parallel and not affect each other. And the most important thing, which is kind of implicit everywhere in each slide of this presentation, is that the results of the compilation from Gradle, they need to be cacheable. So if the build results are not cacheable, then the whole approach is not working. But this is also a good thing to verify, right? So if we are putting this effort, we will see in the metrics that if we see that it doesn't bring any improvements, then there must be something which is preventing from working, right? So preventing from making this impact. And then it requires additional attention to investigate. Now, let's find the metrics that we can measure to confirm our hypothesis. So for me, it was obvious that I was working in the project for already quite some time. I saw this evolution from the monolithic to the modular application, right? And for me, the first natural step was, OK, we have a monolith. Let's try to extract as many things out of the monolith so that the new features don't have to depend on it. And the overall compilation time from this monolith goes down. I hope you can see the chart from there. But basically, it's a burn down chart, right? Which is interesting. It is looking like a burn up in the beginning. And this is actually because of the problem, this process of the modularization. So in the beginning, you start with the very few modules, then you start extracting them, but you do not remove the dependencies on the monolith that you introduced now. So at some point, you have to, cut all the connections with the monolith, and you need to do this work to modularize the app. So this was a simple and kind of natural step for us. And you can see that we did have quite some impact. So we reduced the number of dependencies at least by 20%, but I think the most important learning from this is that we were able to prevent the further growth of the number of modules which depend on the monolith, which means that every new feature that we are going to introduce doesn't need to rely on it. It can just assemble all the platform capabilities that it needs into its dependencies, and then you just work with those capabilities, and you don't really care what's in the rest of the app, right? So you have this architecture, and it helps you to quickly iterate over your things. But as I already mentioned, so let's try to challenge this hypothesis. What can actually demonstrate that our strategy of modularizing the monolith doesn't really work? What if the capabilities that we are extracting, they are not actually picked up or not actually leveraged by our feature teams? So this means is that this is the graph that shows the number of the efforts in our modularization, right? So you can see that if I were to correlate the two previous graphs, you would see that the growth in the number of modules correlates with the drop in the dependencies on the monolith. And what could actually, signal that our strategy is not working? So maybe the assumption that the monolith is causing the whole app to be recompiled for a long time, maybe it's not an issue because maybe it's changed only once a year. So if my hypothesis was not correct, then we would actually see it later and on further charts. And then additional metric, which is not really a code metric, but which is also relevant, and this is what I mentioned in Accelerate, what Accelerate suggests, is to measure the build times, right? So I focused on the code metrics primarily because I didn't have good ways to measure the build times and have reliable data around them. So I have to work around it and to find this information, but I will also explain about the build times a bit later. And so this is the chart I was mentioning. So the number of modules will grow naturally. So just counting how many modules depend on the monolith might not be a good idea. Or how many modules depend on the platform capabilities, the new platform capability module that we have created. So how do we actually show that the capabilities actually are useful for everyone in the team, right? So you see that how the orange line, the bottom line grows. So it's on this graph, it looks almost horizontal, but in reality, it's still growing, right? And the upper line is growing much faster than the bottom line. So you can see these bumps up on the graph. So this means is that we have actually started introducing these new capabilities, and these capabilities are actually being leveraged. So the adoption of the new capabilities is much faster than just the growth of the modules, which means that these capabilities are actually used by the new modules, and they're actually useful for the team. So this guardrail metric, it's a secondary metric, you can say, that helps us to understand that a bigger picture, not just focus on one dimension, but try to expand it a bit more, to be a bit more holistic here. So while this is all good, we did a lot of work. We provided a lot of value to our feature teams who are relying on the platform teams, on the work that the platform team is doing. There are still issues. So we reduced also the number of times the monolith needs to be changed because we moved so much code out of it into the feature modules. But we still saw that the build times are still sometimes slow, not sometimes, even regularly. You pull in the main, you see that, I need to go get a coffee. So the strategy that we are following is working, but not to the extent that we thought it would work. And just looking a bit into the future, so as I said, we didn't have reliable build time metrics when we started. But later, we actually started using Gradle Enterprise. And on this graph, you can see these green peaks, so these spikes. So each vertical line is the build time. And the Gradle explains to you what is the, by color coding it, it explains you what exactly the Gradle spend time working on. So when these spikes, they are of the green color, which means that the Gradle actually spent on the serial execution. So the serial execution means that there is certain bottleneck which prevents your compilation to run in multiple parallel threads. So this means is that although we have created a lot of modules, they all still await for some module which is not necessarily our app monolith. And we needed to investigate. So there is a historical graph at the top, so you can see that there are improvements, but there are not a lot of them. Not enough, or not as many as we would like to see, right? So we did improve the parallelization. So here there is a number which says 6.9x, so which means that degree of parallelization is almost 7, which is good, but we can still do better. So we can still do better, but we need to look deeper into where is actually an issue that we didn't see from the start, And this is the thing that I was saying in the beginning. When the project starts to grow so big, it's really hard to grasp what's happening there without having some sort of the overarching analysis across the whole project. Yeah, I would like to show you some abstract paintings. I would like to say that this is some generative art, but it's not. It's just some dependency graph that I have tried to generate out of our Gradle project. So here I took just direct dependencies. Maybe if you look close, you can try to see, you can find some clusters here, you can find some patterns. Maybe there is this, not sure what is this pitch black, but you can see that there are some parts which are, gravitating towards it. So there is some heavy core at the center of it. And another interesting thing, if we take the transitive dependencies, which is, spoiler, one thing that I have underestimated, how big could be the impact of the transitive dependencies in the project, it looks even more indecipherable. So, just dumping the dependency graph doesn't help on a project with hundreds of modules. So there needs to be some other approach, right? Yeah, we end up with this sort of the illustration. So I call it the wheel of the dependencies. I don't know, maybe a web of the dependencies, black holes, you name it, right? So on a circle, you can see the names of the modules, and you can see the connections between them. And here, it's actually much easier to start noticing the patterns in the application. So you can see that, there are too many inbound nodes and outbound nodes to this module. So this is our app monolith, right? So although we did all of work, there are still many dependencies remaining, right? But you can also see that there are plenty of other modules where there are also a lot of connections. And this is something that we haven't considered. So we need to look actually in detail what's happening there. So this, for example, part of the chart is looking very suspicious. So this is how we came up with a different metrics. So this graph is good for maybe one-time analysis, but you cannot chart it for every week across the year, right? So you would have tons of these abstract paintings, so you would have some weird mix if you try to align them all together. But we can find something which we can actually measure. We called it the module impact ratio. So the module impact ratio, it actually defines how many modules will have to be recompiled if I changed my module. So you can think of it as a stability of your dependency tree. So if something changes in the tree, so how many of the branches, how many of the leaves would have to be recompiled because of this change? And you can calculate it as following. So we take one module, and we take all the dependencies on this module. So we take the direct dependencies, which are easy to find, and then we find all the transitive dependencies of modules, which depend on modules, which depend on our candidate, right? And this is the transitive part is what made the biggest difference in our case. And just to give you maybe an estimation, what is the good ratio, what is the bad ratio? So for example, with the platform API modules, which are supposed to be used across the whole app, so every feature needs, for example, something like network layer, right? Or almost every feature. So it's fine for that API module to be used to have a high impact ratio. But then if you take one feature or a screen, it's meant to be used only once. So you have an app module, and the feature is meant to be included only once in this app module. So we do not allow feature-to-feature dependencies, feature-to-screen, and so on. So if it's something, if number of usages is more than one, or then it's a sign that something is wrong. So maybe you might have maybe a demo application. So in each case, it would be slightly different values, but you get the idea, right? So just to explain a bit about these platform modules and APIs, I already mentioned you the kernel and plugins architecture, and this is the diagram that we are trying to follow. So on the right, we have the features. So you can think of it as a module which contains a single screen, which is composed of different maybe other modules, so which constitute the whole screen. And this screen, it actually makes use of different platform APIs. So you can see that the screen depends only on APIs. It doesn't know anything how the platform API is implemented, so it doesn't know anything about them. And you can see that, so the implementation in the end is going to be used only in the app module. So everyone knows which capabilities exist in the app. They can leverage them freely. So implementation to API is an allowed dependency. Implementation to implementation is not. And because this is the rule in our the project, we can safely say that if it's an API module, then yeah, it could have a high impact ratio. If it's an implementation, then having something higher than, I don't know, 0.1 is already a sign that there is something wrong with the dependencies in this module, or maybe someone is pulling in this module accidentally, or maybe for whatever reasons that exist there. Now, if you remember that the wheel chart, right? So we saw that there are some patterns on it, that some modules are getting a lot of the dependencies, while others are let's say, in a good shape, right? So you can see in this histogram, I charted the values of the impact ratios of all the modules in the project. On the leftmost bar, we have the good picture. So this is our target state. So we have 150-something modules which are included once or maybe twice, depends, right? And this is good. So it means that the modularization strategy is working, and the project is not hopeless, and there is a way out of this, right? Then we have some smaller bars on the right. We have some modules which are heavy, which we should look into at some point. We have maybe one module which has almost everyone uses. And we have this suspicious bar in the middle, like on the second from the left. So we have almost the same number of modules as the good ones, which have the impact ratio of 0.3, which means that whenever one of these modules changes, 1/3 of the app needs to be recompiled. Yeah, which would, of course, will make developers not happy. So why do I need to wait again for the whole project to be recompiled? And this is actually suspicious, right? So I think somewhere here I can't say that it's an even distribution or a normal distribution, but this sticks out immediately, right? So this is something we need to zoom into, and we need to look into the more details. And actually, spoiler, like this was one of the modules, which is not actually a monolith, but it connects many of other modules, and it actually even introduces some dependency cycles due to different configurations, how it is included. And that's why, it's like a magnet which attracts all other modules and then makes them to be impacted when something changes in this web, let's say, or a wheel of the dependency, right? So someone who ended up in this cluster, they would be definitely impacted when something changes in this group of modules. Yeah, and then if we just transform the same graph into different form, right? So this is what I was saying, the good part, right? So 43, almost 44% are in a good shape, so we don't need to worry about them. So let's just skip this part, which gives us the roughly 60% of other modules that we need to look into. And here we can skip this part. So these are the other bars that we saw in the histogram, so we can ignore them for now and focus on this, slice of the pie. So this is where we could have the biggest impact with the lowest effort, right? So the 80-20 rule still applies here, and this is where we want to focus our efforts on, right? If we have limited engineering resources, if we have limited time, we want to make use of the developer's time, we want to make use of the, let's say, project or a product time to get the most out of it. But can it still be better? Of course. You might have guessed throughout the presentation. So I was mentioning that some modules don't change that often. And it means that even if one of the modules has a very high impact ratio, doesn't necessarily mean that it's a bad module or an unhealthy module. And it means that if this module is almost never changed, then we can multiply maybe, as an example, we take the ratio of this module, we multiply by change frequency, maybe 0 to 1. And this module suddenly becomes less impactful, so we don't need to worry about it. And at the same time, the modules which might have these average impact ratios, and if they are changed very much often, then they suddenly become more impactful. And this is the one more reason to look into those modules. So we didn't go into this route because this would be then no longer just the code metrics. It means you need to crunch some data from the Git history, right? So we need to understand which parts are changed more often, which parts are changed less often, and so on. So this could be the next iteration, right? So we are trying to be pragmatic here. We tackle the areas with the biggest impact, lowest effort, and then we move on to the next such area. And this way, we're keeping ourselves busy, and we deliver impact incrementally and iteratively, and making the best use of our time. Yeah, I wanted to end the presentation with bits of the implementation. So initially, I thought I could spend some time on the research. I could explain you to convince you that it's not that big of an effort to actually collect these metrics. But then I realized that I cannot fit both into a single presentation, so I decided to focus on the research. But I also realized that implementation, I think there is nothing special in it. You can all replicate it in your own projects, knowing the structure of your project the best. You would know it better than me, so my code wouldn't help you that much. So I just wanted to mention that, for example, dumping the dependency graph of Gradle was, for me, under 100 lines of code in Groovy. So write it into a file, then later process it somewhere. Same with the collector and all the modules in the project. Then, for analyzing, for example, the graph, you can take one of the graph libraries, and because you're using the library, it would be also less than 100 lines of code to find the transitive dependencies, to find maybe cycles in your data in your graph, and that's it. And then, like storing in a database, I think it's also not something that we would like to look into. SQLite was mentioned multiple times, I think, today. Then we have exposed. I used exposed, and it was easy to write it in SQLite database. And then it's a matter of just write the SQLite query. If you haven't practiced it much like me, like I had to sharpen it a bit, this knowledge. And then I have a query. I can run this query every week. And then I have a website where I show all these metrics. Then I would like to close the presentation with more examples, right? So this is just one of the metrics that we collect at Zalando, and we have other things that we could measure. So when we were working, for example, on modularizing the monolith, the natural question which comes up, what do I modularize next? So how do I find the classes which I use the most and which I should move to get the most out of this task, out of this change? And it's actually is also, you can apply this rudimentary technique, which is also can give you enough of the impact without much effort. So just take all the imports, and you know which file depends on which file. You know which module belongs to the file, so you know which module uses which classes from another module. And this way, the same you can find. Same as we charted dependencies between modules, we can chart dependencies between feature to platform capability, for example. And then you know which class to move to the next. And then once you have the dependency graph, you can also do all sorts of research there. So you can find these incorrect dependencies. You can enforce that API cannot depend on the implementation. And you can also, like all these charts that I actually shown, they are not only the input for our work, but they also the output of our work. We show it to the management. Hey, this is what we did. This is the impact. And this is how we move towards our goal. And the last example is the code ownership. So when you have many teams, it's also crucial to keep track that everything is owned, that teams are accountable for the changes they do. And yeah, this is also becomes rather easy. Just parse the code owner's file, and you're already iterating on the project, and you can also ensure that the code ownership is in place. And that's it. I'm not sure if we have time for questions.